Okay, and this whole course is going to be based on recording actually, and I'll talk about that. Okay, so again, my name is Prasoon, and there's a website, and please, I assume you guys know how to get to my website, right? But I mean, this is important, so make sure you know where to go, and we will be using a bunch of software. So I can teach you guys distributed system concepts in the vacuum, just the algorithms and the abstractions. Or I can have you guys build something. If I'm going to have you guys build something, it might, it'd be good if it's interesting. And he's going to say that nothing is interesting if it doesn't involve graphics, right? and so at least it should require some visual, so that you can. If it's too abstract, an airline reservation system. With some back-end stuff, it's probably that interesting. So I told you I teach two courses, and one of the courses I teach is COM 401, which is this course that our students take, undergrad students take as their second programming course. And it seems natural to go from what they do in a non-distributed fashion to a distributed course. So just to connect these courses, I said, okay, I build this. They build this. They also build over 16 weeks a big project. And what would it mean to distribute that? Okay? So that's kind of how I see these two courses. I see just my life connecting in these two courses. And what would be good is if you could just take a project that already exists and distribute it, so that we know that you are focusing only on distributed issues. You are not focusing on anything else. And if I was to teach you a course on collaborative computing, which I also do, then we build the whole thing ourselves, because the UI is important. Okay, so hey, you just take the UI, you like it or not, and also I'll show you what this guy did. This is an economics major who did this, and when you complain about your projects, just imagine what this guy did. So that's this. I can take his stuff and run it on. So what does distributed mean, by the way? I get into that a little bit later in one of the lectures. But what's distributed? When is the program distributed? So how do you define a distributed program?
It runs on multiple hosts.
It runs on multiple hosts, right? Or it can run on multiple hosts. Because you write the program, there are no hosts at that time. Right? And we don't even know which host there might be. So what's a more technical way? What's a litmus test that this is a distributed program? You've written it's a distributed program.
Maybe you simulate several hosts in your desktop.
You simulate on your own desktop? Mm-hmm. So how might you simulate? So what's the difference between parallel computing and distributed computing?
Shared memory.
Shared memory. Okay. And can you have on one computer non-shared memory?
Yes.
When you run?
Isolated processes.
Isolated processes. So a distributed program is nothing else but communicating sequential processes. Okay? When you do your demos, you'll probably run it all on a computer, but there'll be different processes that talk to each other. Okay? So that's what we'll do. So what I do here is I show you how you can use his project to run multiple instances of an object of a class in the same process. And then what you will do in your project is put these objects in different processes. Okay? So that's what this is about. And this is making less sense, right now. It will make more sense after the demos. But I just wanted to give you the preliminaries. Okay, now he built this fancy UI, fancy stuff, but it was a COM 401 course on programming concepts, not an UI, yet he has a UI. The reason he has a UI is because I built a UI generator called Object Editor, which I give to my students in my 401 class. They just write the objects and they get displayed through my UI generator, and you get interesting user interfaces there. Okay? When he did his project, there was the version of jar file I had was OER 17. Since then, it is OER 22. and you're free to use either one of them. If you have a bug, which I mean, that's not your problem if you have a bug there. So if you just want to use 17, that's okay. It'll give you no warnings. But 22 is the one that's correct. Okay. So I put them both there. Now we talked about getting into the low-level layers. Okay. Typically, the low-level layers are provided to you by software that exists. Okay. And I want you to go and implement some of these layers. And the software that exists today will not let you go and change layers. So for this course, and I hope this is why it was called Awesome, I worked, like a summer and a winter, and I built my own layer stack. Okay. And you can imagine one little bug. There's just so many mistakes possible there. So I had to work quite hard to get it. Okay, and I call it GIPC for Generalized Interprocess Communication. It's got a whole bunch of layers all stacked together, and you just get to see them juxtaposed. Okay, and at some point you will start using this. Okay, if you want to get into this last project, there's just too many other things to be done for you to worry about some of the things I can do for you. Okay, so you will use the system for two reasons. One, you will go and change one layer that I already provide with your own layer. That layer will remain constant in your final project, so it will get really debugged. Okay, and then you will also add a layer to it, which is this atomic fault tolerant. Okay, and you can it's got this group communication. So all the other communication systems provide you with one communication between two processes. It's got a group communication there in it. That will make your life, when you go and do fault tolerant, which we'll talk about, it will make your life much easier. Okay, so it will be interesting to go and see just how I designed it, how I developed it, what concepts there are, and you'll use it. So what I want to do at the end of this class is, for those of you who have laptops, to download this, see whether you can get stuff working. I'm here. And for those of you who don't, you can just join somebody with a laptop, see what issues they have, and get going. Okay? Questions so far? Okay. Sorry, I should be saying one midterm and one final. The reason there's a little confusion here is because the final is going to be like a midterm. It's not cumulative. Okay, it's just done on the final date. Okay. Now you might say, why do I have a final? We're doing this project. Let's just just worry about that. And the fact is that there are concepts here, and if I don't test them, you're not really going to put them deep into your brain. Okay. So then there's the assignments, which is the homework, 50%. We'll do some classwork, and I'll talk about that. And let's just say that's 10%. And then there's a fudge factor, based on class participation, etc. Now, if you do the project and you do average in the exams, you're fine. You'll get some form of H, because the project is not easy. If you don't do the project or really bomb the exam, then you might get some form of P. Okay? But it's been rare for students to get P+, even Ps, because it's hard not to. If you've got a project, and it's got so much weight, it's hard not to get a good grade. Okay? So I wouldn't worry too much. This is a grad course. But I do want to let you know what the weightage is. By the way, you guys can see this properly, right? So you can discuss solutions with each other at a high level. This is stuff you've seen before. Not at the code level, so you shouldn't really be sharing code. And the point is that when you do your project, it should be clear that the code didn't come from somewhere else. So as long as you do debugging together is fine, of course. And what I've done is I experimented with this in the undergrad class, and it seemed to work well. So if I'm going to tell you that you guys can discuss the whole solution with each other at the English level, then because you've got a great friend, you benefit, and you may not, and so that's not fair, right? And clearly there's some learning that's happening when you guys talk to each other. So I've started giving detailed solution in the assignments, and in fine print, saying, read this only when you're stuck. And I've tried to see how much learning really happens when I didn't do it and when I do it. And I just found the students go much further. Students go much further when they when they're given part of the solution, because filling in the blanks is still tricky. Okay, so that's we'll use Piazza for all communication. You know, so if you have a question about your assignment or some personal issue, send me mail. Otherwise, just discuss it on Piazza with everybody else. Don't feel shy that I look silly saying this. No, nobody feels silly. Okay? The fact that you asked a question means you're articulate. Means you and if you have a question, other people will also have a question. So this is the 401 project. Does that make sense to you, this term non-blocking I/O? Anyone?
Asynchronous.
Sorry?
Asynchronous I/O.
Have you heard of some Java library that provides?
Netty.
Netty?
Yeah. And Amina.
Okay. So the Java, have you heard of
Java and I/O.
NIO?
Yeah.
So what we're going to do first is take his project. We're going to start with an NIO tutorial. That is an echo server. Okay, here's a server. Each client can go and get the data echoed. So you get to know how to use NIO. Then you take Boa's project. Okay, you've got NIO, you've got this Boa's project, and you will create a distributed non-blocking simulation. Okay. And have you used NIO?
Yeah, I use it for my current project.
Okay, how easy is it to use?
I have a higher level asynchronous library, and it's not that easy because you don't use regular loops, and you use callbacks and futures, things like this. You think differently. So
yeah, and you're using something high level that's got future in it. But basically, the thing is that at any point, one of many things could have happened.
yeah,
It's not that you're blocked waiting for this thing to happen. So there's a whole state transition you have to worry about. You have to worry about that. If I'm in this state and I've gone to this state from this state, these are my options now. So that's the challenge. And why do we go for non-blocking? What does he want? Scalability. You go for non-blocking because you want scalability. So they really put this layer recently in for scalability. So to that extent, you're getting. And we will see that we'll do it in a non-blocking fashion, in a blocking fashion, and you'll measure the difference, and you'll say, aha, you can see. Okay? So the first assignment, like I said, is taking these two pieces of software and stitching them together, and we're looking at the concepts behind it also. Okay, how was it designed? That's sort of low level. You can think of NIO as being low level, sockets as being higher level. At least you know what to expect next, and even higher level is RMI. RMI stands for
Remote method invocation.
That's part of Java. And the whole idea is that you can invoke a method in a remote address space just as you invoke a method in a local address space. That's the theory. Okay? So this should be easier to do, right? So you'll get to see. No?
Maybe.
Nothing is easy in life. Nothing is easy in life. Okay? You'll have to worry about, the thing is that, I can ask a grad student to do my work, or I can do it myself, right? Which do you think is more efficient?
From whose point of view?
From my point of view.
The grad
A student doesn't matter. I have to explain to the grad student what to do, right? And with today's Eclipse and great debugging tools, I find programming such a pleasure, having dealt with core dumps in C. And so when you're doing NIO, you're starting from scratch. You're not depending on some layer and understanding some layer. With a grad student, I've got to understand what their lifestyle is like. Are they taking, tenacious RA, which means they have no time. They're writing papers all the time. So I have to go and deal with all of those problems. But when I'm doing it myself, I don't have to. So you'll have to go and understand how RMI works. But it's not quite invoking a local procedure. There's 3 sets of lectures of mine on this stuff. And once you understand that, you can write your program. And then you've got to go and tailor your program and architecture to what RMI gives you. So this won't be a trivial thing, but it'll be fun. And you get to see the difference between abstractions. That what did I give up? Systems is about trade-offs. Okay, it's about, do I get to do things efficiently, but perhaps erroneously? Or do I get to do it correctly and maybe slowly? There's a famous saying in compilers, if your program doesn't work, turn all the optimizations off. Okay, because optimizations always have the select. Okay, so you'll do the same task in a second way now. It's like has anybody done a comparative programming language course where you just learn multiple languages in one course? Nobody? So I used to teach programming language course also. And I would have them do a Smalltalk interpreter in Modular, a Prolog interpreter in ML, an ML interpreter in Smalltalk, and all in one course. Okay? And it was fun. It was fun, depending on what fun means. But so you get to do sort of the same kind of thing in different languages. Okay? So by doing the same task here, you get to understand things better. Okay? Now in RMI, what you have is that it is high level. You deal with procedure calls. It's also synchronous. These two things don't have to go together. Does anybody know of a asynchronous procedure call? Maybe that's what you've used. Asynchronous remote procedure call system?
You mean high level?
Procedure. You're invoking procedures directly in another process. You're not sending bytes on an NIO channel, but it's non-blocking.
I use RabbitMQ to do that, but I'm not sure if it is asynchronous.
It's not. So Google has got some APIs that are non-asynchronous. Okay, and what I did in my done is so by the way, these things the previous slide, the communication, there were sockets. RMI is built on top of sockets, and it uses Java object serialization, and then there was RMI here. What I've done is make this layer actually changeable. You can put NIO, you can put sockets, whatever you want. Okay, I use Java object serialization, and that's a separate layer. And then I've got my layer GIPC layer, and this is asynchronous procedure calls. Okay, so you will see that you can still program procedurally. In fact, you will take your RMI program and just run it on GIPC. It'll just run. Just all the stuff will work, and it'll be just how to go and glue the components together. Okay, and here's where you will see that you'll get a performance benefit because there's underneath NIO. So you're not making a trade-off. You're getting non-blocking. The problem is right here. This is what costs. Okay, this is where things slow down. This is something you will then address in the next. You will change the Java object serialization with your own serialization. Do you guys understand what serialization might mean?
Encoding, decoding.
So you've got a data structure to pass from one process to another. It is not shared memory. So you've got to go in, flatten it out, and unflatten it. How hard do you think this problem is?
I think that's very hard. We have a complex network of pointers. We have to serialize.
Small piece of code. But this would be the most challenging recursive program you'll ever write in your life. Okay? It's a recursive program involving different kinds of objects. It's not just, and it'll be fun because, it'll be debuggable. In fact, if you want to, you can just pass strings. So you can debug. But this is going to be, the other projects, the first two projects and GIPC are going to be, doing your learning concepts, but this will really, really be a fun algorithm to write. Okay, you can do it. I've taught this in previous classes, and but so that's what we do. And what we'll do is we'll build a different kind of serialization system than what Java has. Java's serialization system is based on internal memory representation. It's all designed for one language. What you will do is similar to what web services do, which is base the serialization on the interface the object provides, not how the data is stored inside. So you will be able to take a vector and serialize it into an array list at the other end, because they both present the same interface, a list. Okay, so by doing so, if tomorrow you go and program and provide a web service, which is these services that run across the web, you will know underneath what's really going on. Okay? So that's going to be, it's just a very good educational tool to know how to do this, and so that's why I wrote this project. Okay, questions? And then a fault-tolerant atomic broadcast. Okay, so what you will do is you will take your simulation that has been written for RMI, that also happened to work for GIPC, and also happened to work for GIPC with object serialization. So you're seeing all these components nicely separated, and you will just interpose a layer in between that suddenly provides fault tolerance, atomic broadcast, whatever that means. So what do you think an atomic broadcast means? What's a broadcast?
Sending one message to multiple recipients.
So that's multicast. Sending a message. So supposing you're a group, broadcast is sending the message to everybody, including yourself. And broadcast and replication, you see the connection? Right? You want the replicas to be consistent, you broadcast. Fault-tolerant broadcast.
One fails, roll back and do it again.
So what kind of fault are we talking about maybe?
The message loss.
Okay. So, or if the messages, TCP/IP will take care of messages being lost.
But you say it's a broadcast, you may want to use UDP and it can loss.
We'll just use TCP. If you want consistency, we'll use TCP/IP.
Okay.
Okay. Yeah, but otherwise it's trivial. It's a networking problem. Just send the message, say whoever wants to get it. You don't get it, don't get it. Best effort. That's called best effort. Okay. No, we want to make it a distributed systems program. Okay. So we want consistency of some kind. You are getting consistency. Whenever I send a message from one process to another, we will guarantee that every message I send to another process is received in order. So what might it mean to broadcasting is sending the message to everybody? An atomic broadcast might mean?
Maybe everyone receives it or no one receives it.
Okay, that's a very good one. That either everybody receives it or nobody receives it. But we already are guaranteed that the low-level layer will make it go to everybody.
Everyone receives the same replica of the message.
So the message will eventually...
The replica, they are exact replica.
So we want replicas, which means that every message should be processed in the same order at every site. Okay? That's what we want. And fault tolerant, messages won't get lost, but maybe processes might die. And when we do the topic broadcast, we are going to have we'll see how that's done. So how to go and make sure that even when a process dies, the remaining processes just are consistent and can continue on despite that one process dying. So how many processes you can allow to die at the same time is an issue. We'll assume only one process dies at one time. It's not that two guys die at the same time. That's hard enough. Okay? So that's what's going to happen. Okay? And like I said, that's the phenomenon. This project I have not given before. So the fun class may become a very non-fun class at this point. But I did this project about 20 days ago. And then yesterday it suddenly didn't seem to be working. But then I think it was just some button I pressed. So we'll see. It'll be a mystery what happens today. Okay, so we'll see. But that's the goal. Okay, you guys get the idea? Okay. So we've had a lot of discussion on this. When I was teaching the class last time, he was in my class. And he took my collaborative class. And I want to go for an inverted class this time. Okay, what does it mean? Well, I've never taught fault tolerance before. Okay, so the reason I sweated this summer was because I just did it all. And I did it from first principles. There's a lot of algorithms of fault tolerance. I got the basic idea, then I said, let me just implement it myself so that I learn all the pitfalls. And I may not have implemented it, just the most elegant way. I'll find out as I read up on the other algorithms. And that's when I present the lectures. So I will, at the end of the course, provide you with live lectures. But the other projects, all the other projects I've given before. Okay, which means I've also gone and given lectures on that stuff. Okay, now you see here that I'm recording the lecture. Right? So I record all my lectures. Now, when I record lectures in a small class, I might hear your voice might or might not be recorded, but my voice is certainly recorded. So it's not perfect, but it's doable. People can go in and understand from the recorded lectures. Okay, so what I want to do is, and those lectures can be converted into YouTube videos. Okay, and I know the students did go and watch those videos before the exams and before their projects. Okay, so why not just go and do this before coming to class? It requires more discipline from you guys. Okay, and what should we do in class? Well, that's so of course, how do I make sure that Dinesh isn't working you too hard and not letting you study? I give a little quiz at the beginning. Okay, and what we'll do is we'll do a quiz in the beginning just to make sure you looked at the material, got the concepts right. Then and the quizzes will be select A, B, C, D, whatever. I've never done an inverted class before. So here I am teaching two courses at the same time and doing inverted classes on both of them at the same time. So you see, I'm pretty ambitious. Okay, but I've thought about this all summer. And what we'll do then is, we'll discuss why it was answer C and not B. Okay, so that will be the lecture that you've already looked. And this is what people do in case studies for a long time in business schools. That you go and study the case and then we discuss the case later. Okay, but more important, whenever I teach a course on distributed collaborative systems or distributed systems, the code you will write is about 1/10 of what Bo wrote in his class. The trouble is that it is complex. And this is where I think all of you guys being here at the same time and I being here at the same time, we can just make sure that the project happens. Because ultimately, it is the project that matters and the concepts behind the project. And you can just work here. And if you have nothing else to do, you've done your project already, don't leave class, help somebody else out maybe, or do some other work, but just stay in class. And what it does mean, what Prathamesh mentioned to me before, was that it means he says, look, I have to come to class plus look at your lecture. So what do you guys think about that? Am I doubling your work? Because you have to go and look at the lecture on your own time, and then you have to come to the lecture also. What do you guys think? And is that a problem? So the hope is that by coming to the lecture and doing homework here and doing your projects here, your projects are going to happen much more efficiently. That's the hope. Okay? And you will get to sort of exchange ideas with each other. I mean, what happens in my class typically is 15 minutes earlier before class, students are always talking about their projects. And I'm very excited when I hear that conversation because I know they're involved. Why not talk about that during class? Okay. I can always take my lectures and present them. It's the easiest thing in the world for me to do. At breakfast time, I put my recording on. It's in my brain. Play it out. It is so easy that if you guys ever think this is not working, I'm happy to do it. This is from my point of view, this is more challenging. And I have to go and design the quizzes. I have to design, but so what's your instinct? Does that this sounds okay? Fine. And just give your feedback, and like I said, we can always go to another mode. But it will require you to just be very disciplined. And the thing is that you won't get behind on projects, I think, this way. Okay, for instance, the very first thing you have to do is download these projects, and then you have to install the Eclipse thing. What if you don't quite know? I mean, these things can take a lot of time because if you're not familiar with Eclipse, that'll happen quickly. We know at the end of this class, if we have time, is there a clock here? Yeah. You will have that stuff installed. Okay. Actually, we won't. My demos are going to take more than 15 minutes. Okay. So let's get to that now.